Hi, welcome back to Statistics 1. We're up to Lecture 20, and the topic today is binary logistic regression. So the topic of this week in general is how to deal with data sets where the outcome variable is categorical. So in the last lecture, we covered chi-square tests, which we use when all variables, the outcome variable and the predictor variables, are categorical. Here in binary logistic regression, we can have an outcome variable that's categorical, but the predictors may be categorical and or continuous. So I've divided this lecture up into just two segments. In the first segment, I'll give you an overview of binary logistic regression, and then in the second segment, we'll walk through a full example. So in this first segment, I want to talk about sort of the concept of binary logistic regression and how it's different from regular simple regression or multiple regression that we covered a few weeks ago. So as I mentioned, it's appropriate when predicting a categorical variable that's binary, just has two possible outcomes. And from a set of predictors that could be continuous, could be categorical, could be a combination of both. So it's the same exact logic as multiple regression, except now instead of having a continuous outcome variable with a normal distribution, we have a binary categorical outcome variable. So we'll do binary logistic regression here in this lecture, but it's an easy extension to do what's called multinomial regression, which is if we have a categorical variable that has more than two levels. Just for the sake of time, I'm just going to cover binary logistic, but hopefully you'll see how it can be extended into multinomial regression. So here was the formula for multiple regression, which we covered in detail in several lectures a few weeks ago. We're predicting some score y on an outcome variable, but in multiple regression we were assuming a nice continuous variable with a nice normal distribution. Now our y variable is going to be categorical and binary, just 0 or 1. So here's the formula for binary logistic regression. We're going to take the natural log of the outcome variable over 1 minus the outcome variable. And that may look very weird to you, looked very weird to me the first time I encountered binary logistic regression. So we're going to spend some time in this first segment talking about why that's the left-hand side of the equation now in our regression formula. Notice all the other variables stay the same. We have a bunch of predictors, and we're going to estimate a bunch of regression coefficients. But why do we have this logarithmic function over here on the left-hand side of the equation? Well, it's very simple if you think about it. We're trying to predict an outcome variable that can only take on one of two values, 0 or 1. So we have to come up with a predicted score that falls between 0 and 1. And we use the logistic function to do that. So this is the logistic function. So imagine we're trying to predict, say, the diagnosis of some disease that's much more common in, say, elderly adults than in younger adults. So we could have, on the x-axis, imagine we had age. If we're predicting the likelihood of some disease, then if we're actually predicting the diagnosis, then when you're at the lower end of the age distribution, I'm just going to predict a bunch of zeros, and at the higher end of the distribution, I'm going to predict a bunch of ones. So the scatter plot in these kinds of examples will look exactly like that. You'll have a lot of dots down here and a lot of dots down here. So to fit that plot, we need a logistic function. And notice that on the y-axis, we need our predicted scores to fall between 0 and 1. So that's why we have this transformation on the left hand of our regression equation. You might just think, well, why not just calculate the probability of the outcome as a function of all our predictors? Well, there's no guarantee that the linear combination of the predictors will come up with a score that falls between 0 and 1. That's why we need that transformation. So we can think about the probability of the outcome as well as the odds of the outcome, or odds ratio. So an odds ratio is just the probability of the outcome over 1 minus the probability of the outcome. So for example, if the probability is just 0.5 of some outcome, then the odds or odds ratio is an even 1. If we take the natural log of the odds, that's called the log odds or logit. And the logit is what you see on the left-hand side of the equation in binary logistic regression. That allows us to use this set of predictors that are continuous or categorical, and it guarantees us with a predicted score that's going to fall between 0 and 1, which is exactly what we need since our outcome measure can only take on a value of 0 and 1. So the logit is that important transformation that gets us to be able to use this multiple regression technique with this binary categorical outcome. Again, the probability of the outcome is just the odds over 1 plus the odds, and we can think about odds as the probability of the outcome over the probability of the opposite of the outcome. So let's consider an example just to sort of make this more concrete. So if the outcome variable in a binary logistic regression is a faculty member being promoted to tenure, and the predictor variable is how many publications that faculty member has, let's say we got the following output from a regression analysis. Again, let's assume it's standardized just to make that easier. And the regression coefficient is 0.39. What does that mean? Well, remember this is regression. So what that means is for every 1 unit increase in x, that's the predicted change in y. But in this case, that's the predicted change in the logit, which is a little bit abstract and odd. So let's go to the next slide. And remember that we can take the logit, convert it into odds ratios, convert it into probabilities. So let's just do that. We have a logit of 0.39. Well, that was the regression coefficient, right? So a 1 unit increase in x, so 1 unit increase in publications means I'm going to predict a 0.39 increase in the logit. Well, what does that mean in the real world? Well, a logit of 0.39 translates to an odds ratio of 1.48. So that means the odds of promotion are multiplied by 1.48 for every 1 more publication a faculty member has. Again, let's try and make that a little more concrete. Well, if the odds of promotion was, say, 16 publications is 1.27, then the odds of promotion with 17 publications, 1 more, is 1.27 times 1.48, or 1.88. Now we can represent that in terms of probability, which for me makes the most sense. So down at the bottom, publications, if you have 17 publications, that means the probability of promotion is 0.65, because probability of promotion is odds over 1 plus odds, and we already did our odds calculation. So the point of this exercise is that the logit is a sort of difficult abstract concept to wrap your head around. The scale is sort of hard to interpret, but just know that you can take that logit value and convert it into odds ratios and convert that into probabilities, which I think are much more easier to interpret and to make some sense out of in terms of prediction. So with a binary logistic regression, we're going to have a few hypothesis tests, and this is really not that different from a regular multiple regression. So we can look at the individual predictors. So our individual predictors in this regression equation, are they statistically significant? We can look at the overall model, and we can ask, is the model statistically significant? And then we could do model comparisons. To test each predictor variable, we're going to look at the regression coefficient, just like we did with multiple regression. But again, what's more meaningful is looking at the odds ratio. So we're going to convert that predicted change in the logit to an odds ratio. What we can also do in logistic regression, which is common, is called a walled test, which will test the model with the predictor versus a model without the predictor. We can see how well does the model fit with the predictor in and then with the predictor taken out. And that's called a walled test, very common in logistic regression and in more advanced statistics. So to test the overall model, we're going to compare a chi-square with all the predictors in the model to a chi-square that assumes no relationship between all the predictors and the outcome, otherwise known as the null model. Or we can just compare multiple models, and we'll do that with the walled test. Another way to test the overall efficacy of the model is to see how well it classifies cases, right? So we can make a prediction about each individual case in our data set and make a prediction as to whether it's a 0 or a 1, and then we can look at the percentage of cases classified correctly. That's another way to assess the overall fit of the model. So to wrap up this segment, binary logistic regression is appropriate when we're predicting a binary categorical outcome variable from a set of predictors that could be continuous and or categorical. The main components of the output that we're going to look for that allow us to test hypotheses are regression coefficients, odds ratios, and walled tests associated with each predictor, and model chi-square and classification success, which will be associated with the overall model. And we'll look at all of this in the next segment when we walk through an actual example.